Hello, we are group 23, and today we want to share the K-mean clustering algorithm. The K-mean algorithm is a clustering algorithm. The algorithm is aiming at finding K clusters and samples in the same cluster which are most similar. Setting the conception as follows. Our goal is to find the minimum sum of square distance for samples in the same clusters. The basic algorithm and procedure code are as follows. First, randomly select K points from S as initial centroid. Second, calculate the distance between each point and all centroid. Assign them to the cluster with the minimal distance. If no changes occur, end the algorithm. Otherwise, recalculate the centroid for that cluster and repeat step 2. However, using the algorithm as described above needs to calculate distance from each point to all centroid, resulting in a total complexity of ONKL, where L is the number of iterations. When dealing with a large number of points, the algorithm's performance is not ideal. Therefore, one method for improvement is using a KD tree. A KD tree is a binary tree. Building it can be described as follows. First, choose the median of dimension in a dataset as the roots, dividing the data into two parts based on whether they are greater or less than the median. In each subspace, choose a median of another dimension for further partitioning, repeating until all data is partitioned. For a KD tree which is already constructed, the algorithm for finding the current nearest distance is as follows. First, identify the space containing the target point. Calculate the distance between the target point and current leaf node. And using this distance as the radius to create a hypersphere. If the hypersphere's radius is less than the difference between the target point and the coordinate value of the splitting node in that dimension, indicate an intersection between the splitting line and the hypersphere. Explore the left and right subspace divided by the splitting line, and backtrack upward until reaching to the roots. According to current research, the K-means algorithm seems to be an NP-hard problem. In Daniel's paper, for arbitrary dimensions and k equals 2, he transfers the minimum sum of squares calculating problem into an expression as follows, and reducing it to a dense set chart problem, which is NP-hard. Mina's paper also demonstrates that when the dimension is 2, the planar K-means problems can be reduced to planar 3-set problems, which make it NP-hard.
Now let me introduce the improvement of the traditional K-means algorithm. Our target is to reduce the number of distance calculations. And we can find that the triangle inequality is equal to. The figure shows a point X and two centers A and B, which form a triangle. We know that one side of a triangle is not less than the difference between the other two sides. So if we also know that twice the distance between X and A is no more than the distance between A and B, we can draw the conclusion that B will not be closer to X than A. Based on this principle, Phillips proposed two improvement methods. The first one is compare means. After each iteration, we need to calculate and cache the distance between centers. We don't need to consider the center satisfying the following inequality, because it has been proved that it will not be closer to X than the currently located center. This reduces the amount of calculation. The second one is sort means. Different from the first method, this one saves the distance between centers in the matrix k times k and sorts each row. We can search centers in increasing order until the inequality is satisfied. This avoids searching faraway centers, but sorting will generate additional overhead. Based on the triangle inequality, we can also get the boundary of the distance between the point and the center after each iteration. The following algorithms are optimized according to the boundary. Elkins algorithm maintains an upper bound and k lower bounds for each point. The upper bound represents the maximum distance between the center, the current center and x after iteration. The lower bound represents the minimum distance between each center and x after iteration. So we don't need to consider those centers that satisfies one of the following two inequalities, because they are not closer to x than the current center. Harmony algorithm maintains one upper bound and one lower bound. The lower bound is just for the second closest center, and the tightening process is added to the algorithm. If the centers still cannot be eliminated, we need to calculate all the k centers. Compared it with the previous algorithm, it has some advantage and disadvantage. The final one is the Drax algorithm. It maintains one upper bound and b lower bound. The screening principles are similar to the previous algorithms. The choice of b will affect the performance. Experimentally, Drake proposed k divided by 8 is a good floor of b when k is larger than 8. Above is a partial optimization algorithm. That's all.